Hello, this is Jack Hicks, and this is my physics lab report, Magnetic Field of Permanent Dipole Magnets. So as a quick little introduction, the objective is to observe and analyze a system of a permanent dipole magnet at different locations and obtain magnetic field, moment, and distance values at different observation locations. We can do this and calculate the magnetic moment of the bar magnet, visualize the magnetic field produced by the bar magnet, plot the magnetic field versus difference, model it in glow script, and compare the model and the observations. So the main ideas are magnetic field and permanent dipoles. Dipoles being permanent in that they aren't induced, they don't disappear when you take away whatever induces it. And the magnetic field can be found in various different ways. The equation shown on the left, and we will be using the third one in our glow script, and the second one to plot the distance versus magnetic field to find the magnetic moment. So a little preview of the results. First, the system was basically everything and the surroundings were nothing. And again, as a preview, we found a bunch of magnetic field values at different locations, but the important one was the magnetic moment being 9.525 and the D observation location found to be 0.284 meters, and the magnetic field at 45 degrees was 77.77 microteslas. The model had the exact same D and the magnetic field of 65.57 microteslas, which is a close match but not exact. So what model are we using exactly? So we'll be using the Biot-Savart law and to find the magnetic moment of a bar magnet. So by using the law, we can treat the bar magnet as a dipole, and we can calculate magnetic fields at different locations, graph that, and use that graph in the equations below on the bottom left to find the magnetic moment. Once we find the magnetic moment, we can set that in our model and calculate everything else for a model. Now the origin is at the initial position of the bar magnet. We're assuming the bar magnet is in the same position every time. There are no electronics to mess with the magnetic field, and it's a permanent dipole, and these are done for ease of calculations, with the initial values being on the right. Getting into the actual experiment, so there were three parts. First was finding the magnetic field sensor on the phone to get an accurate measurement, then calculating magnetic field at different points, and then calculating magnetic field at 45 degrees. So taking the data and calculating magnetic moment. So first we have all the data that I plugged into the Excel spreadsheet, and what we're really going to use right now is the plot on the top right. So here are the calculations using the plot. Using the line of best fit, we can find K and R and the y-intercept, and then rearranging everything, we can find the magnetic moment, and all the calculations are done, and it was found to be 9.525. So after doing the calculations, we can now get into the code. First, we use the magnetic moment and put it in there on the left, and then we put a function for the magnetic field at any point, which the equations were shown on the first couple slides, and then we put in the distance, and then the observation points along the axis and perpendicular to it, and then we basically put a bunch of arrows to signify the dipole moments, or not the dipole moments, the magnetic fields at different points. Again, here's more of that. Here, making the arrows perpendicular to the observation point, and then finding D perp, and then D, and then reporting those things, as well as the magnetic field at 45 degrees. And here are the results from the code. So let's discuss the data. So for the discussion and conclusions, basically the observed D, the distance, was 0.28426 meters, which exactly matches up with the predicted D from the model. Now the net magnetic field and angle was found to be 7.76 times 10 to the negative 5 teslas, which is close but not exactly the same as the modeled one of 65.57 microteslas, but they are the same in magnitude. And we found the model one by taking the magnitude of the magnetic field found on the left. And the model magnetic field matches the observed one to a really good extent, so that makes sense. Now for some errors, I didn't take into account errors in the app or due to other sources of technology nearby. The bar magnets might not be perfect dipoles, and the sensor location in the phone wouldn't maybe have not been exact, and then there could be rounding errors or experimental errors. So for the additional questions, what if we hadn't oriented the experiment to compensate for magnetic north? Basically, the results would have been off axis and skewed because of Earth's axis. Since it wouldn't be aligned, it would, again, just skew a little bit due to Earth's magnetic field. Now, what if we were to stick two identical magnets together end to end and do the experiment again? It would be pretty much the same except the magnitude would be doubled because we could treat it as one big dipole instead of two. And again, if they're the same length and stuck end to end, it would just double the magnitude. But if it's in the same place and same direction, the direction shouldn't change. Thank you for listening.